Here is a combined summary of the 4 pages. The paper, Towards a Post-Quantum Cryptography in Blockchain, by Tatsuru Kikuchi highlights the need for post-quantum cryptography to attain quantum resistance in blockchains, given the transformative challenges posed by quantum computers. The author emphasizes the gap between quantum key distribution, QKD, and public key cryptography, PKC, citing the lack of mathematical proof for the complexity of reversing mathematical functions used in PKC. QKD's reliance on quantum information theory ensures that any third-party attack would disturb the quantum state, alerting the parties involved. The author then introduces the basic notions of cryptography, including secure communication and exchange of transactions between parties in the presence of adversaries. An encryption scheme is formally defined as a tuple E equals, gen, ens, dec, comprising key generation, encryption, and decryption algorithms. The key generation algorithm is probabilistic, outputting a key chosen according to some distribution, while the encryption algorithm takes a key and message as input, producing a ciphertext. The decryption algorithm reverses this process. An encryption scheme is defined as perfect secure if the probability of encrypting 2 different messages to the same ciphertext is equal. This is formalized in equation 1, and theorem 2.1 states that the size of the key space must be at least as large as the size of the message space. The one-time pad is defined as an encryption scheme where keys, messages, and ciphertexts are bit strings of the same length, and theorem 2.2 states that it is a perfect secure encryption scheme. Shannon's theorem provides a necessary and sufficient condition for an encryption scheme to be perfect secure. Finally, the concept of semantic security is introduced through Attack Game 1, which defines 2 experiments for an adversary to attack an encryption scheme. The adversary sends 2 messages to the challenger, who then encrypts one of the messages using a randomly chosen key and sends the ciphertext to the adversary. The research discusses various aspects of cryptographic security, focusing on semantic security, message recovery security, and parity prediction security. It defines key terms and concepts, including the semantic security advantage and message recovery advantage of an adversary. Theorems are presented, highlighting the relationships between these security measures. The definitions and theorems are supported by examples and experiments, demonstrating the practical applications of these concepts. The research emphasizes the importance of semantic security in ensuring the robustness of encryption schemes against various attacks. It also introduces an efficient probabilistic algorithm and defines a computational cipher, including its components and requirements. The paper recalls the definition of a stream cipher, specifically the one-time pad, and considers a modified scheme where the encryption key is shorter than the message and ciphertext lengths. This scheme uses a function G for encryption and decryption, involving XOR operations. The research aims to provide a comprehensive understanding of cryptographic security, highlighting the significance of semantic security and the efficiency of algorithms in encryption schemes. The research discusses the properties of pseudorandom generators, PRGs, and their application in stream ciphers, emphasizing the importance of PRG security. It introduces the concept of an attack game to evaluate PRG security and constructs a stream cipher using a PRG aiming for semantic security. The paper also delves into block ciphers, focusing on the AES standard, which uses a combination of random key choice and key permutation to ensure security. The block cipher's goal is to behave computationally indistinguishable from a random permutation. The discussion emphasizes the significance of mathematical concepts, such as permutations and their sizes, in ensuring the security of these cryptographic systems. The paper defines the attack game 5 for a given block cipher and discusses the adversary's advantage, VCAD V, A, E, which is considered negligible for a secure block cipher. It also covers the prediction game, key recovery, and exhaustive search attacks, highlighting the importance of a large key space for security. Finally, it defines an ECB cipher as an extension of the block cipher, emphasizing the need for secure cryptographic systems. The research paper discusses the construction of a secure block cipher and the importance of hash functions in cryptography. It describes the block cipher as a tuple of algorithms for key generation, encryption, and decryption. The authors propose enhancing the security of a block cipher by creating an LWISE electronic codebook (ECB) cipher, which is proven to be semantically secure if the original block cipher is secure. The paper also covers the iterated block cipher, mentioning examples like DE and triple DES, which has been superseded by AES due to its higher security level. Hash functions are discussed, emphasizing the need for collisionless security, and a weak collisionless property is defined for practical applications. The concept of an adversary winning a game if two messages collide using a hash function H is introduced, along with the idea of universal hash functions, UHF, classified into UF, statistical UHF, and computational UHF. The paper also delves into trapdoor function schemes, highlighting the RSA scheme as an example, detailing key generation and encryption processes. Throughout, the paper maintains a technical and professional tone, using precise language and domain-specific terminology, mirroring the structure of the original pages. Here is the combined summary. Public key encryption and the RSA trapdoor permutation scheme are discussed, focusing on the RSA assumption and the security of the Diffie-Hellman key exchange protocol. Public key encryption is defined, highlighting probabilistic functions for key generation, encryption, and decryption. The RSA trapdoor permutation scheme is introduced, emphasizing the importance of the RSA assumption, which states that it should be hard for any adversary to break the scheme. The security of the RSA scheme is evaluated through the attack game, where the adversary's advantage in breaking the scheme is measured. The Diffie-Hellman key exchange protocol is then introduced, detailing how the protocol establishes a shared secret between two parties. The security of this protocol relies on the computational Diffie-Hellman assumption, which states that it should be hard to compute the shared secret without going through the key exchange process. The concept of the decisional Diffie-Hellman (DDH) attack game is introduced, where a challenger generates a pair of outputs, U, V, and sends them to an adversary A. The adversary then computes a value W, and outputs a bit B. The event WB is defined as the adversary outputting 1 for a given bit B, and W1 is the event where the adversary wins the game, i.e., W equals W. The advantage of the adversary A in solving the DDH problem is defined as DD hat V, A. CP1 equals P, W0, P, W1, which represents the difference between the probabilities of the adversary winning the game for B equals 0 and B equals 1. The authors then shift their focus to quantum cryptography, introducing basic notions such as qubits, entanglement, and quantum gates. Qubits are defined as the fundamental units in quantum computers, existing in a superposition of 0 and 1. The state of a single qubit can be written as a linear combination of the basis states, 0 and 1. With coefficients alpha and beta satisfying, alpha squared plus beta squared equals 1. Entanglement is introduced as the quantum correlation between different qubits, with the density operator ρ associated with a given qubit state psi defined as ρ equals PSPs. Finally, the construction of multi-qubit systems by taking the tensor product of single qubit systems is discussed, with an example of a two-qubit system provided. In the context of quantum computing, a qubit is considered a pure state if its density operator satisfies the condition ρ squared equals ρ, or equivalently, if it can be expressed in the separable form psi circled times psi. Conversely, a qubit state that cannot be written in this separable way is called an entangled state. The standard basis for two qubits consists of four orthonormal states, known as the Bell states, which are maximally entangled. Quantum gates, such as the Pauli matrices, are unitary operators that act on a small number of qubits, analogous to classical gates. The bit flip gate X, phase flip gate Z, phase shift gate R phi, and Hadamard gate H are essential one-qubit gates that manipulate qubit states. The controlled NOT gate, CNOT, is a two-qubit gate that negates the second bit of its input if the first qubit is 1, and does nothing if the first qubit is 0. Quantum teleportation is a process where Alice sends a qubit to Bob using an entangled pair of qubits. The target qubit is expressed as a linear combination of basis states, psi equals alpha, 0 plus beta, 1. Alice and Bob share an entangled pair of qubits in the Bell state. Psi plus 2 equals 00 plus 11 square root 2. The total state is a tensor product of the target qubit and the entangled pair. Alice performs a Bell measurement, which collapses the state into one of 4 possible Bell states, each corresponding to a classical bit strain. Depending on the measurement outcome, Bob applies a quantum gate to his qubit, resulting in the original qubit state psi. The von Neumann entropy, S, ρ, equals Tr, ρ lane ρ, measures the entropy of a quantum state ρ. The relative von Neumann entropy, S, ρ1, ρ2, equals Tr, ρ1 lane ρ1, Tr, ρ1 lane ρ2, measures the difference in entropy between two states. Holevo's theorem provides an upper bound on the accessible information in a quantum system, applicable to n-tensor product Hilbert spaces, where each subsystem is described by a density operator ρi. This theorem has implications for quantum information processing and quantum communication. The research explores quantum information theory, focusing on Holevo information and its implications on quantum key distribution, QKD. The Holevo information, chi, serves as the upper bound for information that can be known about a quantum state during a Bell measurement. This concept is crucial for understanding the limitations of QKD protocols. The BB84 protocol is introduced as an example of QKD, where Alice and Bob aim to share a secret key by exchanging qubits and using a classical channel for verification. The protocol involves discarding bits where the basis differs and verifying the key through public agreement. However, the BB84 protocol has a loophole, allowing an eavesdropper, Eve, to gain information. The example demonstrates the protocol's protection against passive eavesdropping, highlighting the case where Alice and Bob have the same basis and Eve does not. The authors also discuss cryptographic algorithms used in blockchain, including cryptographic hash functions, symmetric cryptographic algorithms, and asymmetric cryptographic algorithms. They emphasize the importance of understanding these concepts for secure communication. Asymmetric cryptographic algorithms, utilizing public key and private key pairs, provide identity authorization, integrity authorization, source authorization, and support for non-repudiation when used in conjunction with hash functions. FIPS 186 approves digital signature computation algorithms, including RSA, ECDSA, and EDDSA, each with specific key size and generation requirements. ECDSA, widely adopted in major cryptocurrencies, offers higher security compared to RSA, which is less commonly used due to the mathematically hard integer factorization problem. EDDSA, a deterministic scheme, is also approved and used in some cryptocurrencies. Asymmetric cryptographic algorithms are essential for key establishment, which involves setting up keys for communication between entities. SP800 specifies key establishment schemes using RSA and discrete log-based algorithms, including Diffie-Hellman and MQV, for key agreement. These cryptographic algorithms and schemes are crucial for protecting sensitive data and ensuring secure communication. The application of quantum computing in finance is explored, focusing on quantum blockchain-enabled exchange protocols for decentralized systems. The work of Joshi et al. Proposes a quantum blockchain-enabled exchange protocol model, providing a secure and efficient means of exchanging assets in a decentralized manner. Naik et al.'s systematic review highlights the potential benefits of quantum computing in finance, including improved security and efficiency. Stebula et al.'s work on quantum key distribution demonstrates its relevance in decentralized systems, where secure communication is critical. The importance of secure key establishment is emphasized, referencing SP800's approved methods for key agreement and key transport. Digital signatures, used for verification, are crucial in decentralized systems. The cited works provide a foundation for understanding the potential applications and benefits of quantum computing in finance, as well as the importance of secure key establishment and communication in decentralized systems.